Assalamu alaikum, Bismillahirrahmanirrahim. Let's continue our 11th week lecture number 22. In the last lecture, we have calculated different, we have done some numerical of radiations and overall heat transfer through conduction and convection. So now, today we will start furthermore numericals related to the overall heat transfer and also learn some parameter that is related to calculating the overall heat transfer coefficient. So before starting that, you may idea of overall heat resistance. Like in first talk about the conduction. In conduction, we have the formula Ka T1 minus T2 upon the thickness. And if we talk about the in any static conditions, like in construction material in our house, in our homes, in our rooms, so the only changing factor is temperature difference. The thermal conductivity of a material will always the same. The area of the wall and the surface always the same, and thickness of the wall is also will also be same. But the temperature will change with respect to summers and winters and different timings in different daily timings. So if we take this parameter as a overall resistance, then we can write this like this, that Q conduction of the wall T1 minus T2, the temperature difference directly proportional to the heat transfer, and all the fixed parameter like KAL we count it as a resistance, and we place it at a numerator due to the its reverse effect, like inverse effect, sorry, not a reverse but inverse effect, that heat transfer will directly proportional to temperature difference. More greater the temperature difference, greater will be the heat transfer. And we have a inverse relation with the resistance of the wall. The more the resistance, the less the heat transfer. Like if we need to make minimum heat transfer and put insulation and best insulation to have a lesser loss in terms of winters or in summer, we have to put higher resistance. The resistance is makes a resistance to trap the temperature outside or inside. If we talk about the winters, the resistance resists the temperature inside and did not and will not move towards outside, so it gives the resistance. That's the basic idea of the resistance of the wall. And so formula becomes L over K. We have to place resistance over here, the formula will become L over K. Now if we talk about the then from the same idea we can we get the value of R, we get the concept of the resistance, that this resistance make resistance to transfer temperature or transfer heat transfer from one point to another. So similarly we can get the concept with the electrical resistance. Like in electrical resistance, as you can see from this picture, we have two different voltage and due to the voltage difference the current flow. Okay, due to that and due to the resistance there will be different voltage and different and more greater the voltage difference, greater will be the current flow. So the current is corresponding to the heat transfer, and the voltage difference is corresponding to the temperature difference, and the resistance of the material will be the resistance of the electrical resistance. The have major property of the material like like copper, gold, silver. The resistance value of gold is very low, the resistance value of the copper is very low. But if we talk about the non-conductor or bad conductor, the resistance value will be higher. So the resistance will resist the voltage to flow, current to flow, and due to the resistance value there will be difference of voltage. In the similarly, the resistance of the wall is resisting to getting temperature from higher point to lower point, higher temperature to lower temperature. and greater will be the difference, or greater will be the resistance, greater will be the lesser will be the heat transfer rate. Okay, so we get correlation with the resistance formulation exactly with the current and voltage resistance, and we can easily see in the normal home in our home experience. So now move towards the resistance value of convection. The convection formula is Q is equal to HA Ts surface minus surrounding temperature, infinity temperature. So there will be resistance about the Q is directly proportional to temperature, is directly proportional to A and H. We have this coefficient, and the area will remain the same for the wall, and H will also be the same for the particular air. So we take it as a resistance, and we have to write the resistance value on a numerator. So the formula of resistance in the convection becomes R is equal to 1 upon HA. If we place this HA, so we have to divide by 1, and under 1 we can write 1 over HA. So the resistance value of the convection is R is equal to 1 over HA. Similarly, we can write the resistance value for the radiation too. Like in the radiation, we have emissivity, Stephen-Boltzmann constant, and area. This will remain same. The major portion of the heat transfer will be the temperature difference, but in here we have a power of 4, so we cannot directly just make T minus T surrounding. We need to make a similar formula like conduction and convection. As you can see that the formula of whether it is a convection or a conduction, the formula will be the same, T minus T2 or T minus E infinity upon R. So we also, for the radiation, we also want to have the same formula to make overall heat transfer coefficient. Later we will see the overall heat transfer coefficient and overall heat transfer resistance. So we just take this whole quantity as HAS as a heat transfer coefficient for the radiation H, and AS, and this TS minus T surrounding. So we just put H radiation and AS upon this, so it also become 1 upon H radiation AS. If we open the H radiation A, the formula will be sigma emissivity, Stephen-Boltzmann constant, and this will be the HA radiation. So anyway, we will only solve the overall heat transfer resistance for conduction and convection. We will not going towards the radiation because it becomes very complex. Anyway, just write, just have a schematic diagram of this particular example of the wall. We can write the structure, or we can write a resistance diagram similarly like this. You see that if I just close my camera, yes, you can see that we have a surface temperature outside, and we have a air temperature, surrounding air temperature T infinity, and we have a surface temperature of wall T1. There will be resistance of convection heat transfer, and from this T1 to T1 we have a resistance of wall due to the conduction. In conduction there will be the resistance due to their K value, their thickness, their area, so on. And similarly from T point to this we have a resistance of convection. So we can draw the resistance diagram like this: T infinity, then there will be convection resistance, then will be conduction resistance, then will be the convection resistance. We can write this like this. So this is the solved example. So the values are written over here. Like from T infinity to T1 there will be the resistance of 2 degrees centigrade per watt, and from T1 to 2 we have a resistance of 15 degrees centigrade per watt, and then from T2 to this T1 T infinity we have a resistance 3 degree. So if we want to calculate the overall resistance, we can just simply add this all resistance, okay, like this: R convection, R wall, then R convection 2, and we can also open the formula like this: for convection 1 over HA, for conduction L over K, for convection again 1 over H2A. And if we put the parameter over here, that the H value, A value, K and A and H2A, we get the value of R total, the overall heat, overall resistance. Now come towards very simple numerical related to overall heat transfer, overall resistance of the walls and the windows for any different application and problems. Like example 3.2, consider a 0.8 meter height and 1.5 meter wide glass window with a thickness of 8 millimeter and the thermal conductivity of 0.78 watt per meter degree centigrade. Determine the steady rate heat transfer through the glass window and the temperature of its inner surface of the for a day during which the room is maintained at 20 degrees centigrade while the temperature of outdoor is -10. So it's again the example of winters. The inside temperature of the room is maintained to 20 degree and outside temperature is -10, and we have to calculate the heat transfer rate between these two temperature. The outside temperature is -10, then there will be wall, then inside temperature is 20, so there will be heat transfer from 20 degree to -10 degree centigrade. But we don't have a temperature of surface of the wall, so by this resistance concept, we just skip that step. We can skip the step between the heat transfer between from this to this, from this to this, and then this to this. We can directly calculate the heat transfer from this point to this point. Oh, sorry, for this point to this point. This is a high temperature, this is a lower temperature. Anyway, the heat transfer coefficient of the inner and the outer surface window H1 is 10 and H2 is 40, which include the effect of the radiation. So they also include the radiation effect in this H value. Okay. So now first draw the schematic diagram of the glass window. This is the glass window. This is 20 degree inside temperature of room. This is the -10 outside temperature. The temperature will decrease like this. Do the convection, some temperature drop like this, and then there will be temperature drop from T1 to T2, and then there will be temperature difference T2 and surrounding outside -10 degrees centigrade. So yes, we have resistance of convection, conduction, and again convection. So in the paper you also have to draw this diagram, okay, make the schematic. So first of all, we have calculated the resistance of a convection. The resistance of convection is 1 over HA. We calculated the H value is 10 and the area is 1.2 millimeter square. We get the value of Ri inside. Ri means indoor. And the resistance value of the glass, we get the value of length is 0.008. The length will be given in the length is basically thickness. So the thickness of the glass is there. Yes, 8 millimeter. So if we convert that 8 millimeter into meter, so it's now, if we divide by 8 divided by 1000, so it becomes 0.008. okay. So L is thickness basically. K is thermal conductivity of the glass, and then we have area 1.2 meter square. We get the value of resistance of the glass. Then again we get the resistance value of outdoor. This is convection formula, 1 over H2A. H2 is 40, area again 1.2. We get the value of this. If we add all this resistance value, we get the overall resistance of this outside to inside temperature, inside to outside heat transfer resistance values. So we just add all the resistance. Our total will be the point this plus this plus this 0.1127 degree centigrade per watt. Now applying the same formula, that Q is equal to R total, Q is equal to T as T surround T1 minus T surrounding temperature minus T surrounding temperature minus 2 Q is equal to T surrounding temperature minus T outdoor surrounding temperature divided by overall resistance. Yes, Q is direct T surrounding temperature of 20, surrounding temperature of outside minus 10, then R total. We get the overall heat transfer from this point to this point without calculating the surface temperature of the glass windows. It's a very simple numerical you can apply in your daily experience. Just get the thermometer or digital thermometer, or you can calculate the temperature of room inside, and from the same temperature gun or thermometer we can calculate the temperature outside, and you can just the difference of temperature. If you know the material of the wall, the thermal conductivity, you can easily calculate the heat transfer. Okay, now the second thing we need to find out, that the temperature T1. Yes, by this formulation we can also get the unknowns values like T1. So now we get the value of heat transfer. The heat transfer is constant throughout this point. Okay, so heat transfer on the convection will be also will be the same. So the heat transfer of convection is equal to we apply the same formula, that Q is equal to 20 minus T1 divided by resistance of convection 1, like this only. You see that we apply the formula Q is equal to T outside inside room temperature minus T1 divided by resistance of convection. So we know the resistance of convection. Yes, we simply multiply by Q with the resistance of convection, it becomes Q R1. Then for T1, the T1 goes here and this value goes there. So T1 minus T1 is equal to T surface temperature inside of the room minus Q R convection. So 20 minus this heat transfer 266 multiply by R convection, this. If we multiply with this, we get the value of the surface temperature inside the room. You see that it is minus 2.2 degrees centigrade. Even though we just maintain the inside temperature 20 degree, if the wall temperature in the minus, due to the outside temperature is minus 10 degrees, so it transfer the temperature from minus, here we have like temperature 8 degree minus 8, and from here we get the value of minus 2. So the temperature is changing like this. Okay, I hope I hope I clarify the idea of this overall heat transfer. Now in the construction material, some construction material are given by the overall heat transfer resistance, and some material construction are given by the overall heat transfer coefficient. So you know the formula of this, A T1 minus TO divided by resistance. Okay, but here we open the value of A, like A is constant in conduction, convection and radiation, and the remaining portion, like in conduction we have K divided by L, in convection we have only H, heat transfer coefficient, convection heat transfer coefficient, and in radiation we also have radiation heat transfer coefficient HRADS, done previous slides. So we just, in overall heat transfer coefficient, the difference is that we just make the resistance of heat transfer coefficient only. Like induction, the heat transfer coefficient will be in previous diagram, in previous formula, the resistance will be L over K. Now the resistance will be L over K. Okay, because we didn't close the resistance value with the factor of A in overall heat transfer coefficient. So if we make the resistance of only L over K or 1 over H or 1 over H in radiation, we can call this, or we can make the formula of this resistance into U. Okay, so U will be 1 over R, and we call them as a overall heat transfer coefficient U factor. You easily Google U factor, you can get the value of the different construction material of a U factor value. And if you know the U factor value mechanism, you can easily calculate the heat transfer. Like if we talk about the concrete wall, you can Google the U factor value of concrete wall of different mixture, like 2 to 3, 3/4. I don't know about the civil construction very, but I listened something like RCC of 2 into 3 kind of mixture and different mixture of RCC blocks. So you can also get the value of the U value of different concrete blocks, and you can easily measure the area and different temperature inside outside. You can calculate the heat transfer rate. So like I've just shown the some value of construction material U factor value, like exterior wall polymer cracking mortar, this is thickness. If we take 5 millimeter, the U value is 0.930, expanded polystyrene board, calcium silicate, etc. So all are these value of is experimentally calculated by similar formulas, and available in the Google, or it's available, so you can easily calculate the heat transfer. Now we have the you can also, the exterior wall consists of all these things, so we just added it and we get the overall U value 0.099. You just add all the things, so we get the value of U of exterior wall. Similarly, in the roof we have a waterproof material, cement mortar, exterior polystyrene, autoclave, lightweight concrete. We just calculate the V value. Sum of all U values will be the overall U value of roof. You just simply multiply by the overall U value into area into temperature difference, you get the heat transfer rate. Okay, now you get the that both U and resistance will be inverse relation. U, if we want to get the U value from the resistance, is equal to 1 over R, and if we want to get the R value, the R will be is equal to 1 over U. Okay, so if we know the resistance value of different material, we can easily calculate the value of U, and if we know the U factor of different materials, we can also get the overall resistance of the wall or roof or etc. Now these are the R values of different construction material, like outside surface in winter, in summer, inside surface we have very little flow of air, like velocity of air. Outside there will be wind, so the value of resistance is higher, and lower, and if we have a still air, we have R values higher. Okay, plane air surface, vertical ordinary surface, 13 millimeter, 20 millimeter. We sometimes we give the air space between the breaks, like I just also place diagram, like where it's gone, like this. So this is air space. You seen the hollow bricks used especially in UK because of to have an insulation, basically to avoid the heat loss from inside to outside. So in foreign countries there will be utilization of this hollow cylinder blocks having very high resistance value to get efficient operation of building. So it's we have a air space between this air is also a good insulation. you know that H value of the air gases is very low. That's why the heat conduction convection heat transfer is very low. Insulation of glass fiber, different steel sliding, slag, wood stud, nominal, acoustic tile, asphalt, concrete block, different lightweight, heavyweight, plaster, gypsum board. These are the construction material you will be using in your after graduation in actual construction of the material, construction of the building and offices, homes, etc. So you will be familiar with this construction material, and by this taking this class, you may able to easily calculate the heat transfer, and you can easily compare the comparison between two different material, which one is better, even it is expensive, but for the operational life or operational condition it will be better. Okay, let's move towards, and also we have a different emissivity values in radiations. Like we have emissivity values, E effective of horizontal slope, vertical wall positions, and this building material, aluminum foil, ordinary glass. You see that the emissivity value of aluminum foil is very low, 0.03. So by using aluminum foil, right now there's a synthetic construction material available in the market, like Elco bond sheets. You see that in the banks, and if you go to the Share vessel, you see that many buildings should cover with the special sheet type material, that is Elco bond sheet. It is the outside surface is made of aluminum foil, so it avoid the radiation of solar radiation to trap in the inside of building. Okay, now come towards the numerical. This is the basically the wall of the house. Outside we have a, first of all, read out, I don't think we have to read out the whole example. I just explain it in my own words. This is the basically the wall of the house. The outside wall is covered with the let's read out again. Determine the overall unit thermal resistance and the overall heat transfer coefficient, U factor and R value of the wood frame wall that is built around 38 mm 90 mm wood stud. This is wood stud basically, with the center to center distance of 400 meter to, this is center to center is 4 mm distance. 90 mm cavity between the stud is filled with, this is the 90 mm cavity is filled with the glass fiber insulation, so it is filled with glass fiber insulation. The inside finish is 13 mm gypsum board. This is 13 mm gypsum board inside wall, and the outside wall is 13 mm wood fiber board. This is wood fiber board. No, this is wood fiber board, I think. Yes, this is wood fiber board, and 13 to 200 millimeter wood and fiberboard, and 13 to 200 millimeter wood bevel lap sliding. This is bevel lap. You see that this is shape of bevel lap. Sliding plates still constitute 25. We are gone. Yes, the insulation cavity constitutes 75%. You see that insulation is higher than that stud. Stud is used to join these two different plates, or this is gypsum boards. So this insulation is constitute 70% portion, and this stud is only constitute 21, and later it also tell us the 4%. So the stud is taking, if we calculate the area done by the stud, it will be 25%, and the remaining portion 75 is covered with the insulation. Okay, the header constitute 4%, and they can be treated as a stud. I also determine the rate of heat loss through the walls. House parameter is 50 meter, and the wall height is 2.5 meter in Las Vegas, Nevada, whose winter design temperature is -2. The outside, this is outside temperature. The indoor design temperature is 22. and assume 20% of the wall is occupied by the glazing, and in the room 20% of the area is taken by the uh, windows. It is called by glazing. So only 80% of the area constituted with this parameter. So we have to, in the end, we have to count 80% of overall heat transfer. Okay, now it's a long numerical, I think. We will continue in this numerical in the next class, because it takes the lecture time is over now. We just increase the timing with the 5 minutes. So if I just continue this lecture, it will take more than 10 to 15 minutes. So let's solve this numerical in next lecture. But right now you get the concept, the R values and U values, and also the comparison of different construction material of R and U values. And you see that this building, I don't see many buildings in the Karachi or in the Pakistan covered with the insulation. If we have a building like this, this is Jamlon board insulation in the construction material. If we place this kind of insulation, we get the very good performance of the building. If we even in the summer, in the winters, in winter the inside room will be kept heated and have a very comfortable uh, environment to the people. And in the summer, if we run the air condition, so it will not take much energy as compared to without insulation. So till then, Hudafiz, we will cover this numerical in the next lecture. Thank you. Take care.